Many times when dealing with annoying line integrals that look really hard and complicated to do, we can use the fundamental theorem for line integrals, which basically means that some arbitrary function phi exists such that the gradient of phi is equal to the components of f. So pretty much what that means is that if we take the partial derivative of phi with respect to x, it would give us f1. And then same with the y part with f2. So if this function exists, we can find that function, and instead of doing the whole vector field and GFT and then the parameterization, we can simply do that new function that we've made phi at the endpoint and the start point and subtract them, and we'll get our answer. So the first thing we want to do is figure out if that condition exists. So that means we take the first part of our function and we take the partial derivative with respect to y, and the second part with respect to x. Then, if both sides, the left side and right side, are the same, that means this function phi exists and we can use this theorem. Also, we can use this theorem when the curve is path independent, meaning it doesn't matter what path you take as long as you get to the start and end points. So think of the word any curve. When that appears, you can oftentimes just skip the condition step and go straight into figuring out what to do. So you kind of you can kind of start with any partial derivative. I just like to start with x. You set that equal to the first function, and then you find the partial integral with it with respect to x, and then you'll get phi. See, usually with an indefinite integral, you would add plus c. In this case, we actually add some new function that's made up of our leftover variables. So in R2, that would just be like g of y. In R3, it would be g, y, z. I'm just going to cover R3 since that's harder. So with this question here, we have f is equal to this, and it starts at this and ends at this point. What's the line integral of this? So the first thing we'd want to do is say that phi at x is equal to f1, and the integral of this, and the x is of f1 dx, which means that phi is equal to, so then we'll take the first part and we'll do the partial derivative of this. So in this case, what that will come out to be would be, I believe, a sine x plus xz cubed. Simply with here, you have to treat z as a constant, and because of that, you tag along that x. And then the last part is there's this arbitrary function g y of z. So we found our phi, but just not all of it yet. We know there's other missing parts to it. So what we'd want to do is we want to utilize the property that phi of y is equal to f2. Right, so the first thing we should do is take this function that we've just made and take the partial derivative with respect to y. So in this case, what that would look like is putting a 2y sine x, and then look, this part doesn't even have a y, so we can drop it, and then you take, I guess for notation, I'm going to use a subscript to denote that we're using g of y. I think the better way to do it would actually just be to say the partial derivative of this with respect to y. Once we have this, we can now say phi at y is equal to f2, which means we have 2y sine x plus is equal to f2. So in this case, f2 is 2y sine x minus 4. 2 minus 4. And you'll notice that these things are matching, right? Whoa. Looks like the partial derivative of g with respect to y is equal to -4. So what can we do with that? So what we'd want to do in this case is actually take the integral, the partial integral with respect to y, right? And when we do this, we get, oh, look, we found our function g now. We know that g, y of z, is actually just -4y plus some other function that's made up of our leftover variables. So what's our leftover variables now? It would just be z. Okay. So what we'd want to do now, what I do at least, is I like to rewrite my function phi. So y squared sine x plus xz cubed minus 4y plus h of z. Whoa, now what we can do is we can use this property to find our last variable. So we do phi at z is equal to, I believe it would be 3xz squared plus h prime z. And now we'll set f3, which means 3xz squared plus h prime of z is equal to f3. Let me go back up. F3 is 3xz squared plus z. 3xz squared plus z. Whoa, we have two matching things. And then look, we found our h prime of z. So you know that if we take h prime of z, dz, the integral of this, we'd get the original function, right? So using this knowledge, we can do that. We can do this, and then, oh, we know what this is. 1 over 2 z squared. Do we have any leftover variables? No, we've already used up x, y, and z. So all we have now is some constant k. You could call it c, a, b, doesn't really matter. Then you have phi x, y, and z is equal to, and then you get this. All right, so now what we can do now, once we've have our function, is actually the easiest part. We just plug in the endpoint and start point, and we get our answer to the line integral. So what you would do is you'd say phi at b, which would be phi at pi over 2 negative 1, 2, I believe. Yes, that's our endpoint. So it would be 1 plus, I'm just plugging it in this into here, right? So we get sine pi over 2, which is just 1. So you get 1. Negative 1 squared, right, is 1. You get 2, 8 minus 4 negative 1 plus 1 over 2, 4. And you get 1 plus 4 pi 4 plus 2, which then becomes 7 plus 4 pi. So that's our endpoint right there. Let me go back and check the start point. 0, 1, negative 1. So it would be 0, 1, negative 1. And then I think this is that plus 1 over 2, which turns out to be negative 3.5. So if we do phi of b minus phi of a, let me use some good form. There. Okay. The line integral c f dot dx is equal to this, which turns out to be 7 plus 4 pi minus bracket negative 3.5. So then we just get 11.5 plus 4 pi, and that's your answer. Really, the hard part of the problem is just keeping track of what variables you've used and not used and making sure. I don't really even know if this is a perfect form that the professor wants, but this is just the way I do it and it kind of makes sense to me. And yeah, that's pretty much it.